Okay, class. This here is what we call a simultaneous tracing. A simultaneous tracing. This here is all the events, all the recordings that occur during one cardiac cycle. So during one cardiac cycle, we're seeing what happens with the EKG, your heart sounds, the pressures in the chambers, the volume in the chambers, and so forth and so on. So these are all the events that occur during one cardiac cycle. All right. Over here, let's just review the cardiac cycle. The first thing that happens in the cardiac cycle is atrial filling. It's totally passive, no contraction of muscle. Then what happens is that fluid comes into the atria. Okay, so the atria fill. The next thing is atrial emptying, which is the same thing as ventricular filling. Ventricular filling. Okay. Under ventricular filling, you had rapid ventricular filling. And if you recall, that's when I said that basically blood comes into the atria. Let's say it gets a little heavy, a little tight in there, and the door drops. On the right side, it would be the tricuspid. On the left side, the bicuspid. Blood will just rush in there. Then, with the door down, some blood is coming in through the inlet valves, shall we say, into the atria, and it just goes directly in. That's what we call diastasis filling. Some blood, however, in the atria does not want to go in, so you have to squeeze down the atria. Slow ventricular filling, because you're squeezing it slow. Atrial contraction. So here's atrial contraction. So here's ventricular filling, which would be rapid ventricular filling and diastasis. And right here would be atrial contraction, which would be slow ventricular filling. Okay. What do you do next? You empty the ventricles. Okay. All of ventricular emptying is the ventricles have to contract. The first thing is isovolumetric contraction. That is just enough force to come in, just enough force. Let's stick down here. That's just enough force to close the valves. No fluid should go back the other way. If you do, you have prolapse. As we lead to prolapse with regurgitation. Okay. So we go back. So then we have ejection contraction. That's the whole reason the heart's in the chest. And what will happen is blood will just rush out. Ejection contraction. And that blood then on the left side would go into the aorta and on the right side into the pulmonary trunk. And then things will relax, but you still are contracted. So you're contracted, but you're still coming back. So we'll call it contraction relaxation. And then the whole job starts again. All right. So that's what we're looking at. All right. Now, in here, when we're looking at the pressures, so I'm going to go to this here. We're looking at the pressures. This is a left heart catheter, a left heart look when it comes to pressures, what we call a left heart catheterization. Now let's see what I'm talking about. Okay, first of all, here are pressures in the left heart. This would be the left atrium, left ventricle. These pressures are significantly higher than the ones on the right side because the left side sends blood to the rest of the body and the right side only this. So this is what we call a left heart look. Now we're going to furthermore call it a left heart catheterization. A left heart catheterization. Now let me show you where they're getting these pressures from. I come here and we're looking at left-sided pressures. Now this would be done in the heart cath lab in a hospital. The heart cath lab, generally done by a cardiologist or a cardiothoracic surgeon. What would happen is a catheter basically is just a tube that has a hole in it that blood could come up in. And this long catheter is hooked to a pressure transducer which can measure pressure. It's hooked to a pressure transducer which can measure pressure. So the person would be laying on the table. They would have this sterilized, the groin. They would take a catheter and go retrograde of the flow. Retrograde means against the flow, because blood would be coming down this way. So you're going retrograde to the flow. You're taking this catheter, and you can see it because it's radio opaque, so they're doing an x-ray. And then you would come in and position the catheter into whatever chamber you wanted to look at. Whatever chamber you wanted to look at, and just leave it in there and let some pressures be taken. Just leave it in there. See, it's in the aorta, but now they kept pushing this in the left ventricle. Now, what does that essentially mean? That essentially means if we start here at the aorta, we're going to start right here at the aorta. This is pressure, that's time on this axis. Then this catheter wouldn't have been this far in. It would have stopped in the aorta. And in the aorta, pressure would be taken. All right. Now, with this right here, we see a pressure drop-off. We see a pressure drop-off. Now, then we see a quick increase in pressure. I want you to study this. When is the only time you see an increase in pressure in the aorta? And that is when the aortic valve opens. When does the aortic valve open? During ejection contraction. That obviously means this tan area right here. This tan area right here must be ejection contraction, because that's the only time that the pressure would rise in the aorta. Okay? So that means then, if this right here is ejection contraction, right there, that's ejection contraction, then that little sliver right there must be isovolumetric contraction. Because remember, isovolumetric contraction precedes ejection contraction. Isovolumetric contraction. So this right here must be that. That must mean that these are events prior to isovolumetric contraction, which would be events occurring primarily in the atria. Okay? All right. So we know that much, that this is ejection contraction. Now, so we're seeing a runoff from the aorta. When we get into the next blood vessel chapter, here's what we're going to find, that the large blood vessels close to the heart can stretch out. The large blood vessels close to the heart can stretch out. We call them elastic arteries. Because think about it. If the only time during a cardiac cycle that you deliver blood to the body is during ejection contraction, then the pressure would go to zero. The pressure would go to zero in the blood vessels until you got another ejection contraction, and you couldn't tolerate. So the elastic arteries, which are the arteries proximal to the heart, act as what I call a second heart. Because what will happen is you'll fill these up, the aorta would stretch and some other blood vessels, and then they would recoil, and that recoil would keep the blood flowing. By the time they come back and have recoiled all the way back down, then it's time again for another ejection contraction. So in other words, you have a runoff of blood here, then you increase. Now this dicrotic notch here, the pressure in in a valve, the pressure in room 1 must exceed the pressure in room 2 to open a valve. The pressure in room 1 must exceed the pressure in room 2 to open a valve. There's no automatic. When the pressure in room 2, the back pressure, falls back down on the valve, it closes it. So the pressure in room 1 going to room 2, room 1 pressure must exceed room 2 pressure to open a valve. Room 2 pressure, when you push in there, that back pressure closes the valve. Now, there's so much pressure in the aorta that when it closes the valve, it makes it bounce one time. When it closes the valve, it's so much back pressure on that aortic valve, it makes it bounce one time. And that's what causes this dicrotic notch. Then once that occurs, you're back here. Now, if this is ejection contraction, and this is isovolumetric contraction, then look back at your notes. This here must be contraction relaxation. So this sliver from here to here, this must be isovolumetric contraction, ejection contraction, and contraction relaxation right there. Okay? So again, what have we done in this particular? We've put a catheter, we've threaded a catheter up into the aorta and left it there. We've taken pressures. We've seen there's a runoff in pressure in that elastic artery, that aorta. Then you get another bounce of blood. When? Doing ejection contraction. Then all of a sudden, the back pressure in the aorta, because see, remember, that left ventricle here is much wider than the aorta. So when you keep pushing, it's like taking a 12-lane highway and pushing it into a 4-lane. If it's not much in the highway, you can keep going. But eventually, if you keep pushing, you're going to see that there's going to be a backup. And that backup would bounce back down. That aortic pressure is so high, it causes a diachrotic notch. And then the aorta runs off until finally it comes back and you do it again. So that would be looking at the aortic pressure. Okay. Now we go and we're going to push the catheter in a little further. Now we're pushing it in to the left ventricle. So this pressure here, which you see there, that one would be left ventricular pressure. Left ventricular pressure. So let's look at that one for a moment. All right. What do we know? Up here must be atrial stuff. Right here, we're going to start here from what we know, that this sliver is isovolumetric contraction. What does an isovolumetric do? Increase pressure quick. Because think about it. You have a bottle of water, the top is closed, you start pushing hard on the bottle of water and no water can be released, then the pressure in that bottle is going to go up. So this isovolumetric contraction, you're pushing down on the same volume of blood. What you're doing is pushing so much pressure, the first amount of pressure, you're going to close your valve. Because the first amount of pressure would have closed the inlet valve, whichever side it is. In this case, this is the left side, the bicuspid. Then the pressure would keep building. You squeeze it. You can't send the blood out until finally you pop open the outlet valve. In this case, the outlet valve is the aorta. Therefore, you see both pressures the same right here. Why? Because all of a sudden now, the left ventricle and aorta are communicating with one another. Ejection, contraction. They're communicating. So now the pressure is the same until finally the back pressure in the aorta closes the valve and you're backing off pressure now. You're squeezing that, you're down squeezing. This again was contraction relaxation. Contraction relaxation. So then you're back here again. Okay? Now, so we got that part. Let's go back here now to this part. All right. This and this. Now, obviously, this right here, if that's isovolumetric contraction, that means you're filling the ventricles here. Now, the way the chambers work is that the chambers relax as you fill them up to a point. So, in other words, as you pour blood in, the chambers kind of passively relax some. Therefore, even though the ventricle is being filled, it's passively relaxing. I'll call it a receptive relaxation. A receptive relaxation. Now, however, when we get here, at that point, the atria is dumping. So back here would have been rapid ventricular filling and diastasis. But here is when the atria contract and they push so hard in there, the ventricle cannot relax that easily. Right here. Now I'm going to end this right here. We're going to pick it up right there again at that left ventricular pressure.